We're thrilled to have our partner Kudan back to guide us through an interactive workshop. Kudan is a computer vision software company specializing in SLAM software solutions. They offer both visual SLAM and 3D Lidar SLAM for various applications. Without further ado, let's dive in. Hi, Joan.
Hi, Henry. Thank you. It's good to be back for another webinar and to be able to talk more about Kudan's Lidar SLAM and our growing partnership with Ouster. So my name is Juan Wee. I'm the CEO of Kudan USA. And in our last webinar, Ouster and Kudan introduced a joint SLAM evaluation program, which we launched late last year. And we've had a lot of good engagement with our customers, and at the same time, a lot of feedback from our customers that are looking to add or even test SLAM to see if it's actually something they want as part of their product. So as you may already know, simultaneous localization and mapping, or SLAM, as it's commonly referred to. It's a computer vision-based method that allows you to use sensor data, traditionally cameras, but more importantly for today, 3D LiDAR sensors, to create a machine understandable model of the world in terms of a point cloud, and at the same time, use that information that it senses to keep precise track of the location and pose of the device within that space. Okay. Just controlling slides on the other side, so I'll look away from the screen once in a while. So that's what I'm doing. I'm focused on the webinar there. I'd probably recommend that you check out our last webinar. We had an introduction to SLAM and our software. We called it 0 to SLAM in 30 minutes. So what we try to do is we try to provide a package, raw space package, which is the robot operating system package that typical customers can download and load within 30 minutes and have their LiDAR up and running and starting scanning and testing. We covered some of the fundamentals of SLAM and basically how to get set up and started. So I think that would be a prerequisite and a primer for something or for topics that we're covering today. So today, we're going to focus on sharing some of the learnings that we got over the last year and some feedback from our customers and partners. Hopefully this will save you some time and headache and try to get you the best results for your particular use case. I'm happy to announce that we've actually expanded our capabilities. When we initially launched the evaluation, for convenience and just in order to streamline the experience, we kind of limited some of the capabilities of our software. For example, we do not use the onboard IMU of the Ouster LiDAR sensor, which is definitely a unique feature for the device. And we've also introduced some parameters that you can use to tweak some of the SLAM characteristics and performance and so on. So we'll cover that and basically go through some of these elements that we've introduced. Okay, so I'm just going to click through some small sample of, I guess, scans our customers have made over the last year. They cover a wide range of different environments. And we'll look at some of the common parameters that will help you in different situations that will help you get results that are hopefully optimal for that particular type of use case and type of environment that you're actually running in. And so, for example, here's basically a side-by-side scan of OS 164 and an OS 064. It's a little blurry, but essentially the quality is very similar. Here's an office with long corridors, which can be a very challenging environment, especially because with a small space, you're going to get a lot of multipath signals back and a lot of noise. So our software is able to mitigate for some of these type of effects. And then you have unstructured environments, like, for example, this is a small forest that we scanned, or our partners have scanned, basically for forestry applications where you're trying to estimate the biomass and all that. So you need to kind of know, how thick the trees are, how tall the trees are within a given area. And so this can be a very challenging environment for a lot of LiDAR SLAM or SLAM in general, just because of all the features and all the potential noise in these type of environments. But as you can see, the features are fairly distinct. This is actually, if you zoom in, it's actually a very high resolution point cloud. We used an OS1 128, and it probably took maybe 2 minutes walking around this pass that you see to make the scan. So definitely been getting a very good and positive response in these type of environments and areas. Similarly, we've had customers that are looking at scaffolding and construction setup and infrastructure monitoring. And even at larger scales, this is basically a drive around in a small town, just having the LiDAR attached to the top of the car. And then this is an underground garage. So previously with this scan, you had GNSS and IMU that you can use. In underground scans like this, where you're GPS denied, we're relying purely on the LiDAR sensor. And so as you can see, it does scan fairly well. I'll show you an example later on where you actually have multi-level garages, and you'll see basically the vehicle going under, one level under and back up, and you'll see how well the space is captured in those type of scans. Again, going back to a little bit of an unstructured area. So this is a cave. So a lot of mining applications and underground construction applications where you're basically monitoring and capturing the progress of the work. And as you can see, again, this is a GPS denied area, and it captures a lot of the details really well. And this is the example I was talking about earlier. I guess it's a little hard to see, but this is, we started at the top of a parking garage and then proceeded down one level. So you can see this was our starting point right here. We basically progressed along this line, and then we went under one level, and you can see us traversing this level underground and coming back up the ramp to the starting point. And so this type of application where you're doing some navigation and tracking and localization of these type of mixed environments. Okay, so we can categorize, as I can show you, showed you some examples. We can categorize most problems in two ways. So one, a lot of our customers either fall into a mapping-centric application, or they fall into a localization-centric application. And so what that means is that if you're more interested in mapping, then your end goal or result that you're looking for in SLAM is a really high resolution point cloud. You're less concerned about the trajectory and the localization aspect, and you just want basically something that represents the real world environment in high resolution and in detail. Whereas on the flip side, if you're localization centric, that means that you're more worried about understanding the location of a vehicle or a robot within a given space. So you can think of it as robotics applications in a factory. You want to make sure that you know where that robot is at any given time as it traverses within that space. And so in those cases, the map quality doesn't matter as much. It becomes more of an internal element where, as long as the map is good enough that we can track and report back an accurate position, that is the most important aspect that you're looking for in those types of things. situations. Okay, so you can tell in this slide here, basically on the left-hand side, you see a fairly low resolution point cloud. This is sufficient for us to support localization. So you can see the trajectory line of the movement going back and forth. You can't really tell what a lot of the elements are. You can see there's some type of sidewalk, some street, and so on, and maybe a building here. But if you're more mapping centric, then you'd be focused on the higher quality map, like you see here, where you can see the trees, you can see the bushes and the different heights, you can see vehicles, parts of the building, and so on. And so that would be, at least visually, the difference between the two use case requirements. Okay. And then just going back to this example here, this is where you would be more localization centric. So being able to really precisely track movement across the space, both vertically and horizontally. Okay. So again, as I shared earlier, we have taken a lot of feedback from our customers, and we've tried to work with Ouster so that we can provide an improved evaluation experience that kind of gets you a closer experience to our full version of the software, and also maximizing the capabilities of the Ouster Lidar. So one of the biggest highlights is having a built-in IMU on the Ouster Lidar. It really helps with reducing noise and just reducing motion artifacts. So the LiDAR is spinning, and at the same time as you're scanning or carrying around and you make rapid turns, sometimes you'll actually see some blurring as your motion kind of matches the motion of the LiDAR scanner, and so you'll get some blurring. What the IMU lets you do is it'll zero out that blur because you kind of sense that you're turning, and it'll basically create a much more crisper point cloud because you don't have this blurriness. And then we'll talk about some of the key parameters in what you can control. This will help you kind of create a crisper point cloud or better robust localization. And then we'll cover some of the things that, for example, covering minimum maximum distance of the points that you want to use. A lot of the LiDAR sensors have an effective range. So for example, on OS 1, if you look at the precision chart, you're probably going to get the highest accuracy up to maybe 35, 40 meters distance, and then you'll see a little bit of a drop off in terms of accuracy or the precision. So you're up to like 30 or 40 meters, you're going to be in the 1 centimeter range, and beyond that, then it kind of increases to 3 or 4 centimeters. So depending on your application, if you're more mapping centric, then you'd want to limit that and say, okay, I'm just going to take points that are, within a meter from me to 30 meters away, and just use those points to create a point cloud as I scan. And they'll create a much more high resolution, cleaner point cloud for you. The minimum distance here becomes important because you'll probably see with some of your scans, you end up capturing yourself or the test vehicle because the LiDAR sees you. So setting a minimum distance, basically you can kind of create a buffer zone around you. So if you set a 1 meter to 1.5 meter minimum distance, then we're going to ignore everything immediately close to you. And so you won't show up in the scans. And then I'll talk a little bit about the voxel sizes for different environments. And then one of the biggest requests that we've had is basically being able to use the reflectivity data that the Ouster LiDAR is providing. Otherwise, I think people also refer to as the intensity. And so you won't see it as part of the real-time scan, but we've actually are embedding that information when you export the point cloud to a POI format. So when you open it up in your favorite viewer, like cloud compare, you'll basically see the intensity information in those